So, so that means not only the capacitance, you have to find out actually how much var supplied by the capacitor, right. And this 68 to verify the result, that is cross checking, here it is coming 68.8 and here it is coming 68. This is nothing but the only decimal places. If you take all the calculations previously up to 4 decimal places, right, everywhere, here for example, I have taken only up to only 1 digit after decimal places. If you take little bit more, I mean 3 or 4 decimal places, you will find that these two are equal, almost equal, right. Exact you will not get because of the numerical because of so many decimal places. So, if you put, then very close to that, but this shows that your that calculation is correct. And that means from this diagram, if you look at the diagram, that Xc is equal to basically Vr by Ic, right. So, that is that thing, that Xc is equal to Vr upon Ic, that here you have used, that Vr upon Ic. Ic was, it was J 148.13 is the magnitude. So, from that you can calculate, you can see that your results are correct. So, mainly not the capacitor, you have to, you are all of you are in electrical engineering and studying power system, you have to see that how much var actually supplied by the shunt capacitor, right. And that means, so this is hopefully this part is understandable, right. Now, efficiency in the case A, transmission line output by output plus losses. Output is 4500 kilowatt, we are keeping in kilowatt only, right, we are keeping in kilowatt only. So, 4500, then I square R, first case 551.47 square into 0.39, this is what divided by 1000, that is why into 10 to the power minus 3. So, this is also kilowatt, this term is also kilowatt, this is kilowatt, this, so efficiency is 97.43%. And when you connect the shunt capacitor, so it is at the time current was 477.56 into 0.39 and it is converted to kilowatt. So, multiplied by 10 to the power minus 3. So, it is 98.06%. That means, when you connect the shunt capacitor, that transmission line efficiency improves to some extent, right. So, that is the idea. So, this is this numerical we consider for the single phase transmission line, right. Now, we consider a 3 phase example, this is example 2. So, we will consider your 3 phase transmission line, right. So, for this when you are studying all this, what I have decided that first all theories, then 5, 6, 7 examples, right, again theories, such that and also all varieties of problem, such that you will understand as a whole that how things are given, right. So, we have here also we have taken 5 or 6 examples. So, such that things will be more or less clear to you, right. The second one is that a 220 kV 3 phase transmission line is 60 kilometer long, right. The resistance is 0.15 ohm per kilometer and the inductance 1.4 millihenry per kilometer. So, use the short line model to find the voltage and power at the sending end and the voltage regulation and efficiency when the line is supplying a 3 phase load of that A 300 MVA at 0.8 power factor lagging at 220 kV and another one is 300 MVA at 0.8 power factor leading at 220 kV, right. So, you have to find out basically that sending end power, voltage and power at the sending end and voltage regulation and efficiency. So, how to find out that R is equal to 60 kilometer long. So, it is a short line. So, no need to consider charging admittance. So, R is equal to 0.15 into 60. So, 60 kilometer long. So, and it is 0.15 ohm per kilometer. So, 9 ohm. AP is 50 hertz, right. As nowhere it is mentioned, the frequency is not mentioned. So, I have taken the frequency is 50 hertz, right. And X is equal to then 2 pi your what you call 2 pi AF, right. And your your this thing inductance is given, L is given 1 omega L. So, 1.4 millihenry per kilometer. So, 1.4 into 10 to the minus 3 into 60 kilometer length, that is 26.39 ohm, right. Now, part A, just hold on. So, receiving end voltage per phase, that VR is equal, listen, whether it is a 3 phase, when you will solve that, so you will use the relationship sending end and receiving end voltage, you will convert this thing all in per phase basis, right. So, that you should know. So, VR is equal to 220 angle 0 upon root 3. So, 127 angle 0 degree kilovolt, this is as a reference we have taken, right. The 3 phase apparent power is 300 MVA at 0.8 power factor lagging, because it is given it is given 300 MVA at 0.8 power factor lagging at 220 kV means line to line voltage. So, per phase power you have to this thing, right. So, that will come, that will come later. So, cos phi is 0.8. So, phi is equal to 36.87 degree. Now, first you write S is equal to 300 and it is P plus J Q. So, angle 36.87 degree, right, is equal to 240 plus J 180. Listen one thing, that when you are writing current at that time it is minus, but when you write power it is actually convention that it should be P plus J Q, means that you have to write that this indicates, this plus angle with power indicates lagging. I think you at the beginning, I think I might have told you that if somewhere load is connected, right, say this is your load, and if it is P plus J Q, load is consuming power, if Q greater than 0, it is called lagging load, right. If Q equal to 0, it is unity power factor load, right, and if Q less than 0, that is negative, it is leading power factor load, right. So, this is the convention. So, generator just opposite, because generator inject power, right. So, when Q greater than 0, that is Q is positive, that means it is lagging load. That is why here 240 plus J 180. So, Q is your what you call positive. So, it is a lagging load, right. So, do not put a negative, if you put negative it will be a mistake, it will be leading load then, right. So, this is the convention, when Q, if you make load consume power P plus J Q, if Q greater than 0, it is lagging load, if Q is equal to 0, it is unity power factor load, and if Q is negative, that is less than 0, it will be leading power factor load. So, in that case it is trained that it is lagging power factor load, 0.8 power factor lagging. So, that is why 300 angle 36.87 degree, that is equal to 240 plus J 180, and bracket we are writing MVA, because this is megawatt, this is megabar. When you combine this you can write MVA, right. Hope it is understandable. Next is, so I hope you understood, right. So, no, do not put minus here, minus, then it will be mistake, right. Lagging load means it, that Q part should be positive, right. Now, the current per phase is given by that IR is equal to S conjugate upon 3 VR conjugate, that we have seen also, right. Now, per phase, current per phase we are making it, that is why this your what you call, this is 3 phase power 300, that is why 3 we have divided it by 3, right, here it is 3. So, S conjugate upon VR conjugate. This thing for example, I hope you will be knowing this, right. For example, this conjugate business will come at the time of load flow studies, of course, after completing all this transmission line characteristic, performance and characteristic will come to the load flow, but question is that this conjugate thing should be clear. For example, suppose you have been given, just for your understanding, suppose you have been given V is equal to say 50 angle say 15 degree volt, right, it is leading, and say suppose I is equal to given say some 5 angle minus 30 degree ampere, suppose this is given to you. Now, you have to find out P and Q. Now, how to find out? So, take a reference line, right, take a reference line, and from that your this is your V is equal to say 50, this is 50 volt and this is your 15 degree, right, and this side this is the current, I is equal to 5 ampere, current is, this is your reference line, and this side current, that current is 30 degree, then what is the angle between voltage and current? It is 15 degree plus 30 degree is equal to 45 degree, right. That means that conjugate term comes there itself, right. That is why when we write that when we write P minus J Q is equal to V conjugate I, or sometime or otherwise we are writing P plus jq is equal to V I conjugate, right. But generally in our power system studies we follow V conjugate I for easy mathematical derivation, right. So, P minus jq is equal to V conjugate I. This conjugate actually to capture the power factor to capture the angle between voltage and current, that is the power factor angle. So, that is why it is 45 degree, that is why P minus jq is equal to V conjugate I. That means, P minus jq, that your V conjugate, V is equal to you are given 15 angle 15 degree. So, conjugate will be 50 angle minus conjugate minus 15 degree into 5 angle minus 30 degree is equal to 250 angle minus 45 degree. That means, P is equal to 250 cos 45 degree and Q is equal to 250 sin 45 degree, because this 250 cosine 45 degree minus j 250 sin 45 degree. So, P will become 250 cos 45 250, that is 250 by root 2, say what, and this is 250 by root 2, say var, right. That is why this conjugate business come, that P minus jq is equal to V conjugate I, right. That is why here P minus, when we are taking, that means just look, that means we are taking actually P plus jq, that is S, that is your V I conjugate, right. And now if you take conjugate on both sides, then S conjugate is equal to P minus jq is equal to V conjugate I. That means, your S conjugate is equal to V conjugate I, right. That means, your I is equal to S conjugate upon V conjugate, right. So, that is why you are writing that this thing IR is equal to S conjugate upon VR conjugate, the 3 comes because of the per phase. If it is per phase, then 3 will not be there, but 3 phase it is, right. That is why S conjugate upon VR conjugate it is, right. I hope you have understood this, right. If you have understood this one, this concept, then everything will be clear, right. So, this is your reference line, accordingly you draw some reference line you have to take and see what is the angle between voltage and current, that is power factor angle. So, this conjugate comes to capture the power factor angle actually, that means the angle between the voltage and current, right. So, that is why after this, so substitute your S conjugate, that is 300 angle minus 36.87 degree, and the 3 into VR is equal to that 127 angle 0 degree kV. So, its conjugate also same thing, the 127 angle 0. So, it comes actually 787.4 angle minus 36.87 degree ampere, right. This is the current, receiving end current, right. Now, from equation 6, this is the relationship from equation 6, right. So, from equation 6, the sending end voltage magnitude is Vs is equal to magnitude Vs is equal to Vr plus magnitude I in bracket R cosine delta plus x sine delta bracket close, right. So, Vr is known 127 kV, magnitude of I is 787.4 ampere, you convert it to kilo ampere 0.7874 kilo ampere, right, because we will keep here all these things in your what you call kV. R is equal to 9 ohm, x is equal to 26.39 ohm. These are the parameters given, all you have computed. So, cosine delta is 0.8 and sine delta is equal to 0.6, right. So, Vs is equal to Vr, we are kept it in kilovolt plus this current, that we have kept it in kilo ampere, right, we have converted to kilo ampere. So, 0.7874 in bracket all this quantity. So, it is coming magnitude of Vs coming 145.13 kilovolt kV. Therefore, Vs, this is line to line, right. So, L dash L I have made it line to line is root 3 into 145.13, that is 251.37 kV, this is the sending end voltage, right. Therefore, voltage regulation is equal to Vs minus Vr, I missed thing 100. So, and here it is multiplied by 100 actually, right, divided by Vr. So, you substitute Vs magnitude Vr and this voltage regulation calculation, you can use 3 phase, you can convert it to per phase also, answer will remain same. If you divide by root 3, this one divided by root 3, this one also will be divided by root 3, this one also will be divided by root 3. So, it will be your same answer. into 100, you will get 14.26%. Only my request to you that all these calculations I have made it. If you find any calculations, anything calculator error anywhere, you should when you should mail to me, right. And now power loss is equal to current square into R, magnitude I square, current magnitude I square into R. This is, that means 787.4 square into 9 R into 10 to the power minus 6 means we are converted to megawatt, right. This is watt divided by 10 to the power 6. So, into 10 to the power minus 6. So, we are converted to megawatt, this will become 5.58 megawatt, right. Therefore, PR, that is per phase receiving end power, is equal to, this is 300 MVA. So, per phase is 300 MVA is 3 phase. So, divided by 3. So, per phase into cos phi 0.8. So, 80 megawatt, right. Similarly, PS, per phase sending end power, is equal to per phase receiving end power plus P loss. So, 80 plus 5.58, that is 85.58 megawatt, right. Therefore, your what you call efficiency, do not come to this side, this is part B. Efficiency is equal to PR upon PS, that is 80 upon 85.58. So, 93.47%. This is output, this receiving end power means output and sending end power means input. So, 80 upon 85.58 into 100. So, 93.47%, this is efficiency. Now, part B. Part B actually root 3 VR IR is equal to 300, this 3 phase MPa. So, VR is 220 kV, IR 787.4 ampere, right. So, you can calculate from equation 6, the sending end voltage magnitude is this is the relationship Vs is equal to Vr plus I, again and again not uttering that mod or magnitude, understandable, I into R cos delta R plus X sin delta R. So, substitute all these your per phase values, right. So, your magnitude of Vr is given, magnitude of I is given, kilo ampere we have converted, Rx known, cosine known, sine known. So, you will get your what you call sorry here it is second, no, this is sorry, this is your next one. So, next one is here, sorry, this is actually, this is the previous one, sorry. So, this is root 3 VR I 300, VR is equal to 220 kV. So, IR is this one, right. Now, it is load is 0.8 power factor leading, right. So, previous page you skip, right, leading. For leading power factor load, equation 6 can be written as. So, as a leading power factor I told you this sign will be minus, right. So, rest will remain same. So, Vs is equal to this 127 plus this one. So, magnitude Vs is 120.2 kV, this is your phase voltage, that is line to neutral. Therefore, Vs line to line is equal to root 3 into 120.2 kV, that is 208.2 kV, right. So, voltage regulation is sending end voltage minus receiving by 220 to 100. So, minus 5.36, that means for leading power factor regulation is negative, that means you can find out the receiving end voltage actually greater than the sending end voltage for the receiving end whatever power factor we have chosen, and per phase real power loss is equal to 787.4 square into 9 into 10 to the minus 6, that is 5.58 megawatt, right. That is PR is equal to per phase receiving end power, that is 80 megawatt, right. Therefore, per phase sending end power PS is equal to PR plus P loss, easily you can compute. So, PS is equal to this much and efficiency is equal to PR upon PS, that is 80 upon 85.58. So, 93.47%, right. So, this is for that your what you call efficiency, right. So, for leading power factor you can see that it is not always, but in this case the regulation is negative, right. So, next example. So, derive the efficiency and regulation of a 3 phase 150 km long 50 Hz transmission line delivering 20 megawatt at a power factor of 0.8 lagging and 66 kV to a balanced load. The resistance of the line is 0.07 ohm per kilometer, 1.57 outside dia, space equilaterally 2 meter between center, use nominal pi method. That means, you have to compute here inductance, capacitance, those formulas are needed, right. So, this is the problem given, right. So, as we will listen to this recording thing, right, if little bit of error making calculation error or little bit of error, in the classroom students can correct, right, everything. So, everything we can rectify, but in this case that is why I am telling, if there is any error, any mistake you find calculation of this that, you please inform, right, because it is recorded. So, that is why this problem you come to this, that R is equal to convert, everything is given. So, it will become 11.25 ohm, because this data is given. Diameter of the conductor is 1.5 centimeter. So, radius is equal to 0.75 centimeter. So, R is equal to 0.0075 meter, distance 2 meter equally, right. So, this formula already derived for inductance chapter. So, L is equal to 2 into 10 power -7 into, you make it to 150 kilometers. So, 150 into 1000 meter, right, natural log ln 2, that is the equilateral your what you call, it is given here, that is your what you call the outside the spaced equilaterally 2 meter between center, right. So, it is d is equal to 2 meter, d is equal to 2 meter. So, d upon your what you call this 0.0075, right. So, that is coming 0.1675 Henry. So, and this one x is equal to 2 pi f into, then you find out into L is this much. So, 52.62 ohm. Similarly, it is 150 kilometer line, long line. So, you have to consider charging capacitance. So, directly that go to the capacitance your chapter, it is 2 pi epsilon 0. So, 2 pi 8.854 into 10 to the power -12 farad per meter, this one epsilon 0 divided by natural log ln 2 upon 0.0075, it is 0.0075 into 150 into 1000, it comes 1.49 microfarad after calculation. And your admittance y is equal to charging admittance y is equal to j omega c. So, that means y is equal to 50 hertz. So, j 2 pi f into 1.449, it is microfarad. So, 10 to the power -6, it is mho. I am not writing Siemens here, I am making everywhere I am putting mho, right. So, y is equal to j 468 into 10 to the power -6 mho, right. Therefore, y by 2 is equal to j 234 into 10 to the power -6 mho. Now, z is equal to r plus jx, r is this much, this is x. So, 53.809 angle 77.9 degree ohm. Now, root 3 Vr, this is line to line, I have marked it by green, when I am making it I missed it, that is why root 3 Vr, it is line to line, IR cos phi is equal to P is equal to 20 into your 1000, right. So, that means root 3 into 66 into IR magnitude is equal to 20,000. So, from which we will get IR is equal to 218.7 ampere at 0.8 power factor lagging, right. So, receiving end voltage Vr will be per phase 66 by root 3 38.104 kV. This is the receiving end voltage Vr, right. Therefore, from equation 15, right, from equation 15, just hold on, you know that Vs is equal to 1 plus zy upon 2 Vr plus ZIR, right. So, IR is known, current is lagging 218.7 angle minus 36.87 degree ampere. So, convert it to kilo ampere 0.2187 and this is the angle kilo ampere. So, Vr is equal to this is 38.10 angle 0 degree kV. So, Z and Y both you have computed. So, ZY by 2 you make it, because 1 plus ZY by 2, ZY by 2 you compute, it will be this one, right, minus 0.0123 plus j 0.00264. Therefore, Vs is equal to, this is 1 minus ZY by 2, because it is coming 1 plus your ZY by 2. So, ZY by 2 is coming this much. So, 1 minus 0.0123 plus j 0.00264 multiply by your Vr, that is 38.104 angle 0 degree plus Z into IR. So, this is Z and this is your IR. So, this is kilo ampere. So, this one will become, also this drop will become kilovolt. So, it is coming Vs is equal to 47.15 angle 9.54 degree kilovolt. This is your Vs, right. Therefore, Vs line to line is equal to root 3 into 47.15 angle 9.54 degree. So, it is 81.66, it is 8.3 angle 9.54 degree kV. So, using equation 9, right, when your charging capacitance was not considered, at that time Vs minus Vr upon Vr, but at the same time we have derived that equation 9, because for the short line A is equal to 1, but here it is not. So, using equation 9 only, it is mod Vs upon mod A minus mod Vr upon mod Vr, right. So, A mod A you can easily calculate your this thing. This is actually A is equal to 1 plus zy by 2. So, this term actually you compute, and this is actually your A, this term, this is the bracket term, this term is A. So, you compute. So, that mod of this is 0.9877, right, minus 66 divided by 66. So, 25.26%, that is the voltage regulation. Now, power loss per phase is equal to magnitude I square R. So, substitute all the value and convert it to megawatt. So, that is why multiplied by 10 to the power minus 6. So, 0.538 megawatt. So, per phase receiving end power 20 upon 3 megawatt, and per phase sending end power is equal to receiving end power plus loss 20 by 3 plus 0.538 megawatt. So, PS is 7.20, efficiency is equal to PR upon PS. So, 20 upon 3 divided by 7.204 is equal to 92.54%, right. This is your what you call efficiency, right. Next example is that determine the voltage, current and power factor at the sending end of a 3 phase. It is another type of problem. 50 Hz overhead transmission line 160 km long, delivering a load of 100 MVA at 0.8 power factor lagging and 132 kV to a balanced load, right. Resistance per kilometer is given 0.16 ohm and inductance per kilometer is given 1.2 millihenry, and capacitance per kilometer per conductor is 0.0082 microfarad. You have to use nominal pi method because line is 160 km long, right. So, in this case you calculate R, it will become 25.6 ohm, X you calculate, it will become 60.3 ohm. Now, all these things not repeating because understandable now. Y is equal to you calculate your your 0.0082 microfarad is given, and it is 50 Hz your what you call that frequency. So, and line length is 160 km. So, you will get J 4.1 into 10 to the power minus 4 mho. I am not using Siemens, using mho, right, and Z is equal to R plus J. So, this is your impedance of the line, angle is 67 degree, right. Now, phase voltage at the receiving end VR is equal to 132 by root 3. So, 76.21 angle 0 degree kV, because this is given, right. Receiving end current IR is equal to your basically it is your what you call it is keeping MVA. So, this side your what you call this side also. So, it is IR root 3, this is where it is given 100 MVA. So, it is making we are making is volt ampere, and this is 132 into 10 to the power 3. So, kilovolt is made volt. So, IR is equal to this one divided root 3 into 132 10 your 10 to the power 3, that is coming 437.38 ampere, right. Other way also you can calculate, no problem, right. So, load has lagging power factor, that is delta is 36.87 degree because it is 0.8. Therefore, current IR is equal to 437.38 angle minus 36.87 degree ampere. So, it is your what you call it is your ABCD parameter you have to calculate. So, first A is equal to 1 plus zy upon 2, first you compute zy by 2, put all this value, you will get this value, right. Then from equation 15 Vs is equal to 1 plus zy by 2 Vr plus ZIR, right. Substitute all this, right, all this current, this is actually volt divided by 1000, that is it has been made kilovolt, right. So, and because this is in kilovolt 76.21 angle 0 is kilovolt. So, that is why this is volt, because this is in ampere and this is divided by 1000. So, Vs is equal to 101.07 angle 8.18 degree 0.18 degree kilovolt, right. So, sending a line voltage multiply this one by root 3, it is 170.05 and this is the angle, right. This is actually it is actually my writing mistake, it is actually 8.18 degree, right. And from equation 17 you calculate Is, your CVR plus DIR, all these things you this thing what you call this thing all you compute, right. So, I have only computed directly, right. So, if you compute all, it will become this value 4.094 into 10 to the power minus 4 this one, and 1 plus zy2 will become like this, right. Then you substitute in that expression, all these things you substitute, only this one you divide by 1000, make it kilo ampere. So, divide by 1000, right, because this voltage is actually in kilovolt, right. So, you will get 414 angle minus 33.06 ampere, right. So, now this is your reference line, this is the voltage, sending end voltage, its angle is 8.18 degree leading, and this is the current, this is minus 33.06. So, this is your 33.06. So, you have to find out the power factor of the sending sending end. So, angle between sending end voltage and sending end current is 8.18 plus 33.06. So, that is why I am writing 8.18 plus 33.06. So, sending end power factor angle is 41.24 degree. If you make it like this and draw it, there will be no mistake. So, sending end power factor cosine of 41.24 degree. So, that is 0.752, right. So, thank you.